I want to thank the organizers for inviting me to this workshop. Of course, Trento is nicer in person. I intend to make myself a pasta dinner one of these evenings just to capture the flavor of the place itself. I have been really enjoying the talks. I think this is a great series precisely because it brings together experimentalists and theorists who are interested in these issues of systems near and beyond the drip line. So I'm going to discuss, I guess, the simplest system beyond the drip line, the neutron-neutron system. And as Hans indicated, this is work that I got involved in during my recent sabbatical at the Technical University of Darmstadt. And it involves, so my part in this was to help with theoretical work in support of an experimental proposal, which is led by Tom Allman. So this is the team, and this is the paper. I want to highlight the role of Matthias Goebel, who's a PhD student working with Hans Werner, and who really pushed all of this through. So, all right, so the basic idea here is to measure the neutron-neutron scattering length using neutrons that are loosely held by the helium-6 nucleus. So you essentially strip away the alpha particle, the neutrons then sit there in some low energy configuration, and you use a precise measurement of the final state neutron energy spectrum to extract the neutron-neutron scattering length. So what I'm going to do is tell you first a little bit more about that in some detail, not much because it's only a 15-minute talk. I'm going to then shift quickly away from experimental details on which I am not an expert by any means, and talk about controlling the theoretical uncertainties in that extraction of the neutron-neutron scattering length. And for those of you who know me and know Hans Werner, it will come as no surprise that the tool that we chose to do this within is so-called halo effective field theory. So I'll describe how that works for helium-6 and why we think we can get the uncertainties here under control at a level where we can say something useful about the neutron-neutron scattering length. So what would it mean to say something useful about the neutron-neutron scattering length? Well, the neutron-neutron scattering length, there is no direct measurement of this. The datum that is extracted from 3 or even higher number of hadron reactions. So there are 2 primary sources of information that go into the so-called recommended value, which I've listed down here. Those are results on Nd breakup and results on radiative pion capture from deuterium. And the radiative pion capture, the most precise radiative pion capture number, which is indicated here by the dashed lines, is in good agreement with a measurement from tunnel of Nd breakup, but it disagrees with other measurements from Bonn of Nd breakup. And I want to emphasize here that the theory that was used to analyze the Nd breakup is the same in both cases. So this is not some issue of different models being used to do the extraction. This is a fundamentally an experimental disagreement between, say, this number and this number. So you might think, well, you know, it's not bad, minus 16.5, minus 18.6, you know, that's like, so first I'd point out that the error bars don't overlap. So there's clearly something here that we don't understand. But more importantly, I'm going to say that the so-called strong proton-proton scattering length sits exactly in between these 2 numbers. So indeed, the sign of charge symmetry breaking in the nucleon-nucleon interaction is fundamentally affected by whether the answer is up here or down here where the recommended value presently sits. So we'd like to essentially settle this, which side of the proton-proton strong scattering length are we on? And that's what Tom's experimental proposal, Tom et al., I should say, there are other people involved too, Tom et al.'s experimental proposal seeks to do by bringing in a completely new source of information on the neutron-neutron scattering length. So because I reside in America, I have learned the so-called bottom line upfront strategy to talks. So this means that I'm going to tell you everything you need to know, and then you can decide if you want to listen to the rest of the talk. So here's the idea. So you take helium-6, which as a theorist I depict this way. There's some amplitude, which is essentially the wave function for that nucleus to separate into a helium-4 and 2 neutrons. And the idea is that, in this case, this is done in inverse kinematics, but you have a high energy helium-6 beam. It impinges on a proton target. You detect the proton and the alpha in kinematics where you can be confident that the alpha suffered quasi-free knockout. And this, as I indicated on my first slide, results in the neutron-neutron pair being left behind. And at that point, they sort of propagate to the target with the bulk of their motion being that they inherit the center of mass motion that the helium-6 had because it's in inverse kinematics. And then what you're really trying to measure then is the distribution of the relative energy. So in this kinematics that I've chosen here, that would be as a function of little p, right? You're trying to measure the distribution of neutrons as a function of that. And the idea is that this neutron-neutron final state interaction leaves a strong imprint on that final state energy distribution. So here is the experimental setup. This experiment is now approved at RIKEN, and the proton and the alpha are detected in a TPC, and then the neutrons fly down here to this wall in the nebula detector, which have excellent energy resolution, which is of course key since, as I said, the bulk of the energy is the center of mass motion of the 2 neutrons, and you're trying to live off detecting the spectrum as a function of relative energy. But the simulations indicate that this is very doable to have a finely binned enough neutron spectrum that you can pick up the effects due to ANN. So the first thing that I want to say about the theory side of this is that you are not measuring the imprint of ANN on the structure of helium-6. So if you do, you can't do this in the experiment. You can't, suddenly there's no switch at the experimental control room where you switch off final state interactions. But in theoretical calculations, you can switch off final state interactions and ask what the spectrum looks like. And so this is the answer. If we switch off final state interactions, then this is the neutron, the density of neutrons as a function of energy. This is the neutron-neutron energy, relative energy, which you'll note is very low, just going up to 1 MeV. And if we switch off FSI in our calculation, then there's very little change in the spectrum. You could go all the way to the so-called unitarity limit where ANN equals infinity, and this would still look very similar. But if you switch on final state interactions, the first thing that happens is that the density gets much larger, meaning that the final state interactions are a big effect here. I'll come back to that point right at the end of the talk. Final state interactions are a big effect here, as you'd hope if you're trying to measure ANN. And then because they're a big effect, the imprint of ANN, you see here we're varying from the let's say, smaller in absolute value number through the recommended number to something that's more towards the infamous dineutron, right? So if you do that, you see marked changes in both the height and, if you look very carefully, the position of the peak. So it's not sensitive to helium-6 structure. It's not also sensitive to, let's say, higher order terms in the effective range expansion for the neutron-neutron amplitude. So the impact of the neutron-neutron effective range on the spectrum is very minimal, as you can see in this figure down here. But it is sensitive to the neutron-neutron scattering length. So this spectrum will do exactly what you want. It's a clean measurement of the neutron-neutron scattering length. But of course, the question, this was all calculated in a specific theory with certain other settings, choices for helium-6 structure. So we need to answer what those choices do in terms of the theory uncertainty of this calculation. So as I'll indicate, we actually used a variety of theory tools to do this, but the one I'm going to focus on for the next 5 minutes is HALO EFT. So HALO EFT is an attempt to organize the physics that is built into cluster models into a systematic expansion. So the underlying physics assumption is exactly the same as in a cluster model of helium-6. It's the degrees of freedom helium-4 and the 2 neutrons. The idea is that if you probe helium-6 with a probe whose wavelength is much larger than the size of helium-4, but is on the order of the size of helium-6, that will be an effective description of the helium-6 nucleus. So as in any effective field theory, there's an expansion in a ratio of scales. So in this case, the ratio of scales is the size of the helium-4 core to the size of the halo. And this approach is how would I say, generic to all halo systems. It's been used for 1 neutron halos, 1 proton halos, and 2 neutron halos. It connects the physics of those halos to the physics of the lightest nuclei, the deuteron, the triton, helium-3. So the halos that have been tackled using this approach are the S-wave 2 neutron halos that have been tackled using this approach are listed at the bottom of the slide. And in fact, because the physics of these systems when viewed in this way is dependent only at leading order on long wavelength properties of the interactions, you can actually put all of these halo systems on the same plot and compare their properties and develop a universal understanding of these S-wave 2 neutron halos. And if you want to know more about this, you should ask our session chair, who has done a lot of work on this, on manifestations of quantum universality in 2 neutron halos. So helium-6 is, of course, not an S-wave halo, it's a p-wave halo, in the sense that the neutron alpha interaction is dominated by a p-wave resonance. So we need a Lagrangian for our effective field theory that includes p-wave interactions. Since the title, since I said I was going to do effective field theory, I have to show a Lagrangian, but now having showed it, I'm going to move on. So the Lagrangian is used to generate an amplitude for N alpha, which is indicated here. It's the amplitude turns out to be the amplitude from the effective range expansion. This amplitude is organized in powers of the small parameter. So in this case, the small parameter, the R over lambda, where R is the size of helium-4 and lambda is the wavelength of the probe, shows up as products of K times R, because K is related to the Broglie wavelength. And by analyzing this amplitude in that spirit, we can see that because the effective range in this system and generically in the p-wave effective range in neutron scattering should be of order 1 over the range of the interaction, that these two terms, in the presence of resonance, these two terms will dominate over the unitarity term. So the organization here is that these two terms form the leading order piece of the amplitude, and the unitarity term, as long as you're not on resonance, as long as you're away from resonance, the unitarity term will be a perturbative correction. So helium-6 as a 2 neutron halo looks like this. There is a separation of scales. The leading order description of helium-6 is done in a Faraday formalism, in which the N alpha amplitude is, as I discussed on the previous slide, as written there, and the S-wave amplitude is just the leading order term in the effective range expansion. At higher orders, we include, as I already indicated, the unitarity correction to the p-wave amplitude. We include the range correction to the neutron-neutron amplitude, and we include the effect of higher partial waves in the N alpha system. So the question that people always ask me is, well, don't those partial waves have a big impact on the structure of helium-6? So the answer to this question, as you'll see in a few slides, depends on the momentum scale at which you look. Before I say that, I need to tell you how we reproduce the helium-6 binding energy. And I think this is one of the beneficial features of Halo EFT, is it allows you to separately identify the impact of different observables on helium-6 structure. So we solve, as I said, in a Faraday or STM formalism, for the amplitude for helium-6 to break up into helium-4 and 2 neutrons. But if you do that, you discover that helium-6 is, the Hamiltonian is unbounded from below. And so as you increase the cutoff on those 3-body equations, the 3-body binding energy goes to infinity. So the solution to this, as realized in the S-wave 2 neutron case by Badaki, Hammer, and Van Kolk, what is that, like more than 20 years ago now, is that you need to introduce a alpha neutron-neutron interaction to stabilize the system to prevent against what in this case is the P wave equivalent of Thomas collapse. And so that parameter that tells you the strength of the three-body interaction is changes as you change the cutoff. But the parameter changes in such a way that the binding energy of helium-6 is held fixed. So the binding energy of helium-6 is reproduced no matter what we do to the neutron-neutron interaction, and no matter what we do to the neutron-alpha interaction, we always get the, whatever that is, 0.97 MeV binding energy of helium-6 with respect to the three-body breakup, correct. So if we go back to the energy spectrum now, so here's again is the energy spectrum in this theorist's limit where you switch off final state interactions. The blue band here is halo EFT with a error band constructed according to the power counting, the ratio of the, so I converted from coordinate space to momentum space. So now I'm doing the neutron-neutron momentum divided by the breakdown scale of the theory. And the green circle indicates the region that we are interested in for this experiment at RIKEN, the energy where the neutron-neutron pair, the region where the neutron-neutron pair has an energy of less than 1 MeV. The other lines on here are different models for helium-6. One is a local Gaussian model done using the Boris code. And the other one is a Yamaguchi model, which is also solved in this fat AF momentum space type way, but where the interactions have finite range and in some cases higher partial waves too. So the point here is that all of those lines on the curve include a selection of NLO effects, but they're not even the same NLO effects. Some of them have higher partial waves, some of them don't, some of them have unitarity pieces, some of them in the P wave, some of them don't, and they all fall within the error estimation of the EFT. And I want to take you back to the key point here is that if you look below 1 MeV, relative neutron-neutron energy, the impact of ANN on this spectrum is even not visible on this plot. So this is the notation here is that this is minus 20.7, this is the recommended value, and this is minus 16.7. So you can't even see the difference. Okay, so, but of course this, you know, I said right at the beginning that the FSI changes the spectrum markedly. So how do we include that? To assess theoretical uncertainty in the inclusion of FSI, we took two different approaches. One is based on the so-called enhancement factor technique, which was developed in the 60s and 70s. So this is an enhancement factor based on the Yost function, and the results for that are indicated by the dashed lines. And the other one was based on explicit computation of the Muller operator for neutron-neutron FSI, and I've given the formula for that on the slide. So because the second is admittedly, it's a three-body problem. We've only included one two-body FSI, but there are kinematical reasons why that would dominate. So we trust that second one more than the first one. But as I will now indicate, it doesn't even matter if you don't trust the second one more than the first one, because if you divide by the shape of the spectrum at the nominal value, you can probably already see this on the slide, then the sensitivity to how you implemented the FSI goes away completely. So the point is that the relative change in the shape compared to the recommended value is robust under different implementations of the FSI, because the change in the shape is exactly that. The peak gets higher and moves to lower ENN, and that is true no matter how you implement FSI. All right, so I think my time is basically up. So let me finish with a couple of perspectives for improvements in this calculation that we hope to have implemented before the data comes out of the experimental effort. The first one is that while this robustness under treatment of FSI is reassuring, it doesn't really constitute an error estimate based on how well we've dealt with FSI. So Hans Werner, myself, and Matthias have started working on an EFT treatment of FSI. This is cikonal-like. It's based on the fact that you're talking about high energy particles in the final state, high energy meaning in this case, the relative energy between the helium-4 and the neutron-neutron pair is large. And this allows you to make arguments about exactly this dominance of neutron-neutron final state interactions that, you know, at some intuitive level, we all know is true, but you'd like to quantify that dominance in terms of an error estimate. So there's some discussion about this on this slide. I'm happy to say more in question time if people are interested. And then the other thing is that while this leading order halo EFT wave function for helium-6 indeed encompasses the results of phenomenological wave functions, we would like to do better. And so there are results on an NLO calculation of helium-6 produced by my student Arben Tapalia a few years ago. And Matthias and Hans Werner and I are interested in collaborating on implementing these corrections at NLO in the calculation of the FSI spectrum to assure ourselves that below 1 MeV relative neutron energy, things really are accurate enough with respect to the wave function. But I don't think that, honestly, that this is a big issue because the ANN dependence of the wave function is small. So this is a useful thing to do for reassurance, but I don't see this as being a source of any problems in terms of corrections to the theory we've already produced. So with that, I am done. I want to emphasize that Halo EFT is a very useful tool for this kind of analysis because it's a systematic way to treat weakly bound nuclei, which establishes universal correlations between different observables and allows you to independently dial in your theory the helium-6 binding energy and the neutron-neutron scattering length and basically anything else that you want. And it tells you which quantities impact observables at which accuracy. So for instance, here, we knew before we started, based on the scales, that the higher partial waves in helium-6 were not going to be of, the other partial waves in helium-6 were not going to be of great importance for what we were doing. These things I've already said. I said this. This very little dependence on the helium-6 structure or the regulator once we renormalize to the binding energy, or the neutron effective range. We're working on improvements. And lastly, I'm going to say that binning the data in the momentum transfer would also reduce the theory uncertainty and provide a check. All right, and with that, I will stop. Thank you for your attention.
So thank you, Daniel, for this very nice overview. I think we have time for one question. Robert?
Just naively wondering, the advantage of knocking an alpha out of helium-6 versus knocking a proton out of a triton is just helium-6 is much.
Oh, I'm glad you asked. That's an excellent question. So indeed, the experimental proposal also includes discussion of doing exactly that. Right? So there are pros and cons from the theory perspective. I think from the experimental perspective, Tom's not here, but he can comment on that better than I could. I think you could do either. From the theory perspective, the expansion, the Halo EFT expansion for the triton doesn't converge quite as quickly because the triton is more deeply bound in that sense than helium-6. So we expect leading order to be a more accurate approximation to the full result in the case of helium-6. So that's one reason we focused on helium-6. I think another reason was practical. I think to some extent this experiment was, how to put it, it's the cousin of experiments to look for a tetraneutron. So that's one, the genesis of the experiment was such that there were reasons to do helium-6. But yes, I think it would be great to do this with triton as well, and compare, right, to see, because then you really have confidence that your treatment of these nuclei that act as neutron-neutron pair holders is good and that you're independent of the neutron-neutron pair holder.
Okay, I don't see any more questions. So thank you again, Daniel. And then let's move on to the next talk by Mac Atkinson, who will tell us about the dispersive optical model.
Okay. I think you have to stop sharing your screen, Daniel. Yeah. Okay, you see my presentation?
Yes.
Can you hear me?
Yes.
Yeah.
Okay. Yeah, thanks for inviting me to this workshop. It's been quite interesting. So I'm going to talk about something that was mentioned in the first day a little bit, the quenching of spectroscopic factors. So I'm from a postdoc at Triumph right now. So the motivation for this first is, I guess I'll briefly discuss a spectroscopic factor. So you can see on this plot on the left, I'm showing two curves. The red curve is a calculation of this E'(p) momentum distribution using a mean field calculation, or a mean field for the quasi-particle orbitals and some optical potential for the outgoing proton. And you can see it overestimates the data quite a bit. So what's done typically is then this curve is scaled until it hits the data like the blue line does. And the scaling factor that's used for this is what's called the spectroscopic factor. And there's more physical explanations for what this factor is, and I'll get into that a little bit later in the talk. But the question that I'm trying to address in this talk is the quenching of spectroscopic factors that was observed by Tosteven and Gade in this PhysRes paper in 2014. So you can see that it's plotted as a difference in separation energy of neutrons and protons, but this sort of quenching trend can also be thought of as more neutron asymmetry is introduced. It seems that the spectroscopic factor is quenching or decreasing. So this is sort of the question I want to address. So before getting into it, I want to introduce the model that I use, which is the dispersive optical model. So here, first I need to discuss what a Green's function is, or single particle propagator. So it's as I have written on the screen here, with this first part being a particle addition contribution to the single particle propagator, and the second fraction is the whole part. So there's some interesting information encoded in here already. So the poles of these each of these terms corresponds to the excitation energies of the A+1 or A-1 nucleus, depending on the particle or whole characteristics. The numerator for these fraction corresponds to a transition probability to the given excitation. And there's actually the numerators are referred to as the spectral functions, which you can extract from the Green's function by taking the imaginary part of it. And it has a close connection with experimental observables. So I'm showing here on the bottom right a histogram, which is an excitation spectrum coming from this calcium-40 E'(p) experiment. It's an excitation spectrum of the resulting potassium-39 nucleus. And in this case, this is the L=2 state, which is the ground state of potassium-39. So you would expect naively that there would just be one bar in this histogram right at the excitation energy, because that's where the quasi-particle energy of the proton being removed from calcium-40. But in fact, you see significant fragmentation of the strength, so this is a log scale. So indeed, most of the strength is contained in that peak at 0, but there's also non-negligible fragmentation of the strength, which is direct evidence of correlations in the nucleus. And this is exactly what the spectral function is as well. So there's a good connection with experiment in this single particle propagator. So how can I calculate this? This is a pretty complicated expression, as I have written in the top of the slide. So you can use perturbation theory to derive the Dyson equation that I'm showing diagrammatically on the right, where the double lines correspond to the full propagator, the single line corresponds to the free propagator. And there's a new object in here, this sigma star, which is the irreducible self energy. This is like a one body object that encapsulates all possible interactions in whatever system you're looking at. This is, of course, in an exact way. This Dyson equation is an exact expression. So now the approximation that gets introduced is in the self-energy itself. I'm going to approximate it by an optical potential, where so I use the same sort of functional forms that have been used over decades of optical potential that have shown a lot of success. And I explicitly include a non-locality, which is a slight tweak on what's been done in the past. This non-locality is parameterized by this factor beta, which sort of controls how far off diagonal this my self-energy will be. And so the question is, it's obvious that this will describe positive observables like scattering differential cross sections, as is done for a while now. But can this also describe negative energy observables? And so, of course, it can, using the dispersive correction that I'm showing here in this box, where the real part of the self-energy at a given energy, it can be found from this dispersive integral of the imaginary part of the self-energy over both positive and negative energy domains. So this is really important because it constrains the self-energy at all energies, both positive and negative. So this ensures that both bound and scattering quantities can simultaneously be described. And so this is where the name dispersive optical model comes from. Okay, so as I mentioned, I'm modeling the self-energy as a phenomenological optical potential. So it involves parameters. So the sort of process to achieve this self-energy would be to initialize some set of parameters, construct your Hartree-Fock and imaginary part of the self-energy, apply this dispersive correction to get the real part of the self-energy, and then you calculate observables, calculate the chi-squared, and determine if a minimum has been reached. If not, you alter the parameters and continue the cycle until some kind of convergence has been reached. And then you can feel confident that a self-energy has been found. So here's just an example of this fitting process for calcium-40 and what's involved. So first we have proton elastic scattering differential cross sections, as well as neutron scattering cross sections, and for energies ranging from 10 MeV up to about 200 MeV. Over the dots on these figures are the experimental data, and the lines are the corresponding DO and fit. So also included are analyzing power data for protons and neutrons, which tells about the sort of spin orbit aspect of the optical potential. Also included in the fit is a proton reaction cross section, as well as neutron total cross sections. So everything I'm showing so far is scattering observables in the positive energy domain. So we also fit negative energy observables, such as the charge density here. So you can see after reproducing all of this data, we can feel pretty confident that a calcium-40 self-energy is found that is suitable to describe various interesting aspects of the nucleus. I did the same sort of fit for calcium-48 with all positive observables and negative energy observables. So now that these nuclei have been fit, I can proceed now to address the main question of the talk, which is once again the quenching of spectroscopic factors. So one way to look at this is to directly calculate this reaction that's done in order to look at spectroscopic factors, which is the E'-P. So that's shown diagrammatically here on the right of the slide, where an electron comes in, strong enough to interact with the nucleus and actually eject a proton from the nucleus, and then there's the resulting A-1 nucleus, and this, the outgoing electron is a different momentum now. So in order to calculate this, I used the distorted wave impulse approximation. In particular, Carlotta Giusti's DWIPI code was very useful for this to interface with the DOM code in order to calculate this cross section. And the DOM provides all ingredients, both the bound state of the nucleus in the A, or of the nucleon of the proton in the A nucleus, as well as the outgoing proton. And you of course need the final state interactions to be included, and that's included in the form of a distorted wave of the outgoing proton. So the DOM provides a completely consistent calculation of this cross section. Whereas in the past, often the bound state was calculated from some fit Wood-Saxon to the experimental radius of the proton, and then separately the outgoing distorted wave was calculated with a different optical potential. But now with the DOM, it's all consistent. So you can see the results of this calculation is presented in these momentum distributions of both the 3½ plus potassium 39 state and the 1½ plus potassium 39 state, which of course correspond to the two least bound orbitals in calcium 40. So this is at an outgoing proton energy of 100 MeV. So you can see the agreement with the data is quite good. And I want to emphasize here that these data were not involved in the DOM fit. The only data involved in the DOM fit were what I showed in the previous slides. So this is coming directly from this self energy that we found fitting the data that I showed previously. Okay, so the same calculation can be done. I guess I need to also point out that this spectroscopic factor comes directly from the DOM self energy. It is not found by scaling to the data as is done in the past. So this comes basically from a derivative of the self energy at the corresponding quasi-particle energy. So yeah, this just to reiterate that all of this comes directly out from the DOM without any scaling or fitting needed of these E'(P) data. So the same can be done for calcium 48. And you can see a very similar agreement with the data. And so now if we compare the spectroscopic factors calculated for calcium 40 and 48, you can see that especially in the D3², there's a significant decrease in the proton spectroscopic factor as you go from calcium 40 to calcium 48. Again, the same number of protons, is the only difference is there's 8 more neutrons in calcium 48. So if you have a lower spectroscopic factor, it means that your system must be more correlated. So why are we seeing that protons are more correlated in calcium 48? So one way to look at this is to look at the single particle momentum distribution. So here's an example of calcium 40's momentum distribution, which is found just by a double Fourier transform of the density matrix. So highlighted in blue here corresponds to momentum above about 270 MeV or 1.4 inverse Fermi, which corresponds to sort of high momentum content, what's beyond the sort of Fermi surface in the nuclear matter picture. And what's important here is that there's a non-negligible fraction of high momentum content in calcium 40. So the amount of high momentum content that is revealed in this momentum distribution is very much connected with the calculated proton spectral functions in calcium 40, where you can see that all the strengths of these levels is distributed over a wide range of energies, whereas in a naive picture, in the independent particle picture, you would expect to only see delta peaks corresponding to the quasi-particle energies of each of these orbitals. But in fact, we have a distribution in strength. And so it's actually out here at these large negative energies, you know, from minus 60 down to minus 100 that a lot of the correlations are manifested. And it's that strength that directly corresponds to this high momentum content we're seeing in this momentum distribution. So these correlations actually correspond to short range correlations. And so it's actually known that these correlations are sensitive to the asymmetry in a nucleus, where this calculation or this experiment done by the class collaboration shows that for nuclei with more neutron excess, there's a higher proton fraction of high momentum content, or of short range correlation pairs. And so this can be, you can think of this as being a consequence of the NP interaction being stronger than the NN or p.p'a interaction, which means that there's, so if there's more neutrons available to form NP pairs, this would mean there's more high momentum content because there's more short range correlation pairs. So this is, sort of consistent with the DOM momentum distributions. As you can see, the blue is the calcium 48 momentum, and you see there's more high momentum content if you compare these two distributions. So to bring this back to the spectral function picture, this is the total spectral function, and this is the peak here. This delta function corresponds to the spectroscopic factor. And so if there's more strength at these continuum energies, if the protons are more correlated, there will be more strength at the continuum energies, meaning there will be strength pulled away from the spectroscopic factor, which is consistent with the idea that the spectroscopic factor is going to be quenched as you have more neutron excess, because your protons will be more correlated. And if you put these numbers that I've calculated with the DOM on this plot, you can see that they're pretty consistent with the trend that's noticed in this in all these different removal reactions. Okay, so it seems that the NP dominance picture of short range correlations is consistent with is definitely a significant piece of the puzzle for what's going on with the quenching of these factors. So with that, I want to summarize that the DOM can describe scattering and bound state observables with the same model, same interaction potential. So it provides consistent descriptions of E'(P) and calcium 40 and 48, and then this high momentum content is one of the things responsible for the observed quenching of spectroscopic factors. And thanks for listening. I'd like to thank my collaborators, both at WashU and NICEF. Thank you.
Okay, thank you, Mac, for this interesting talk. We have time for some questions. Daniel?
Nice talk, Mac. I think the results are really quite impressive. Can you remind me what nucleon potential you were using here?
I didn't use a nucleon potential. This is an optical model for the self-energy.
So then how do I understand the source of the nucleon correlations if I, like, for instance, the NP dominance is driven by one pion exchange?
Right, yeah, so it's you can't trace it back to a use of a nucleon interaction. It's rather the fact that we have this model for the nucleus, which is then constrained by all the data I showed earlier in the talk. And from these observables, it's able to constrain the total self-energy, which in principle is an exact object if calculated with every single diagram. So it's revealing that the data that's being used to constrain this optical model is enough in order to show these more subtle features of what a nucleon interaction would reveal as well.
So then when you calculate E prime P, I assume you're using a one-body operator for the current?
Yes. Yes, that's wrapped up in the distorted wave impulse approximation that I used.
Right. So in general, I can make unitary transformations to move strength from the interaction into the operators. I'm sure you've read the recent paper by Tropiano and collaborators describing how you would understand these phenomena with soft potentials. So I wondered if you wanted to comment on that perspective in your approach.
Yeah, I think so. Yeah, it would be harder to, right. So the distribution of the moving of strength from high momentum to low momentum would, in principle, you would see the same, observable as far as the calculating the spectral function that Nikev has, the Nikev group has measured. But if you try to then look at see how the single particle momentum distribution looked and sort of try to think about the relation there, yeah, I think you wouldn't see the same momentum distribution because, as you said, the strength has been moved around, but in such a way that observables themselves will not be affected.
Sure, because it's unitary. So,
Right.
yeah. Okay, so yes, so that would mean that the interpretation in terms of single particle momentum distributions is dependent on where you choose to sit in that space of unitary transformations.
Yeah, I would agree with that. Or being able to use it as a tool at least is dependent on how you're using how you're moving the interaction around.
I think that's fine as long as everybody's picking the same point in the space.
Yeah.
So comparing, proverbial apples with apples. And not
Yeah,
having
in principle, the best thing is to
some other
observables.
Right. So yeah. Okay. Thank you.
Then we have another question by Chloe.
Hi, very interesting talk indeed. I had a question about your DOM analysis of calcium-40. So I understood that you didn't adjust the spectroscopic factors, but somehow you had some uncertainty given on it. And I didn't see uncertainty band in your fits. So I was wondering where it's come from.
Yeah. So to calculate the uncertainty of the spectroscopic factor, what we did was using, the self-energy is a phenomenological self-energy, so it was fit to data, and the data that we're using have error bars, and so in order to get a sort of estimate of what the error should be on the spectroscopic factor, is we did many refits of the data where we shifted the data within their error bars in order to sort of explore the space a bit more, and the resulting spectroscopic factors that we get after doing all these variations give us the error bar that we have presenting in the spectroscopic factor.
And so all your potential parameters have also some uncertainty, I guess. The parameters of the DOM, I mean.
Yeah, in principle, the model itself has some uncertainty, but we didn't directly calculate this uncertainty. We just use the error bars from the data to guide us.
Okay, thanks.
Okay, so I think this might also be an interesting point for the general discussion, but let's move to the next and final talk of this session, which will also be given by Chloe, and she'll talk about Halo EFT analysis of knockout reactions of beryllium-11 and carbon-15.
So can you see my slides?
Yes.
Yeah, so, okay, so I would like to start by thanking the organizers to give me the opportunity to talk in this very interesting workshop. And what I'm going to talk about today is, what I'm going to present is a Halo EFT analysis of knockout reactions on beryllium-11 and carbon-15. So both beryllium-11 and carbon-15 are halo nuclei. They are both located in the light neutron-rich sector of the nuclear chart. And they are peculiar because they exhibit a very large matter radius compared to their closest neighbors. And this very large size is due to the presence of one loosely bound neutron away from the rest of the nucleons. And they're often seen as a compact core with one neutron in the halo. So as my title says, I'm going to talk about beryllium-11, which is seen as a beryllium-10 compact core with a one neutron in the halo, and carbon-15, seen as a carbon-14 compact core with one neutron in the halo. So these nuclei are very short-lived, so they are studied through reactions. And I'm going to talk about one neutron knockout reactions. So let me define what are these reactions. So they correspond to the dissociation of the halo nucleus into the core and the neutron, and only the core is detected after the collision. So these reactions have very high statistics thanks to the loose binding of the core and the neutron, between the core and the neutron, and also due to the fact that the neutron is not detected in coincidence with the core. So knockout reactions can give you a lot of information. I'm just going to illustrate one information that you can get just by looking at knockout observable. So here you have the typical knockout observable, which is the momentum distribution of the core after the one neutron knockout. So the black square corresponds to the distribution of beryllium-10 after the one neutron knockout on beryllium-11. And the white square corresponds to the momentum distribution of carbon-14 after the one neutron knockout on carbon-15. So these reactions are measured at pretty high energy, usually above 60 MeV per nucleon. And at this energy, you can assume that the reaction is sudden, meaning that you can assume that the distribution that you're measuring after the collision would be similar to the one that the core had inside the nucleus before the collision. So if you combine this sudden view with the uncertainty principle, you know that if you measure an hour distribution, this means that the nucleus was spatially extended. So you can really relate the width of the distribution with the size of the projectile. So in this case, you can see that beryllium-11 has a narrower distribution than carbon-15, and this means that beryllium-11 is more spatially extended than carbon-15. So let me quickly say a few words on how we model these reactions. So we don't model each nucleon separately, but we simplify this many-body problem into a three-body one, where there is the core, the neutron, and the target. And we use an effective interaction between the core and the neutron. And to simulate the projectile target interaction, we use optical potentials, so which contain an imaginary part. And the theoretical cross-section, so the theoretical knockout cross-section, are obtained by summing over all single particle orbital the probability of the occupancy of the single particle orbital times the single particle knockout cross-section. So this probability of occupancy of a single particle orbital is the spectroscopic factor that Mac was talking about in the last talk. So knockout cross-section have two contributions. The first one comes from the diffractive breakup, which corresponds to the situation where both the core and the neutron survive the collision. And the second one is the stripping contribution, which corresponds to the situation where the neutron is absorbed by the target. So in this work, we compute the diffractive breakup contribution with the dynamical cikonal approximation. So as its name indicates, it's a dynamical model, meaning that it includes the dynamics of the reaction, and is also a model relying on the cikonal approximation, so this high energy approximation. And the stripping contribution is computed within the Husson-McVoy model, which relies on the usual cikonal approximation, which has a provides an adiabatic description of the reaction, meaning that the dynamics of the reaction is neglected in this model. So let me now explain how we model the halo nucleus. So Daniel already introduced halo EFT, so this will simplify this slide. So we model the halo nucleus within a halo EFT approach, and as Daniel explained, this approach uses the separation of scale that there is between the size of the core and the size of the halo. And in our case, if you use this approach at next to leading order, we can build a core neutron effective potential, which has two parameters, V0 and V2, and some Gaussian depending on parameter R0. So R0 represents the scale of the short-range physics neglected in the Halo EFT description. And the two parameters, V0 and V2, have to be constrained. And at next to linear order, the S and P waves have to be constrained. And in this work, in some other works that I'm going to talk about a bit after, these parameters are constrained with the experimental binding energy of the ground state and excited states, but also with the asymptotic normalization constant predicted by ab initio calculation in the case of beryllium 11 and extracted from transfer data for carbon 15. So before comparing to data, I just want to explain how this knockout observable are sensitive to the description of the ground state wave function. So on the left, you have the beryllium 11 ground state wave function, which reproduce the asymptotic normalization constant predicted by a no-causal model with continuing calculation. And if you use this ground state wave function, you can compute the diffractive breakup contribution to the knockout of beryllium 11 and the stripping contribution to the knockout, the one neutron knockout of beryllium 11. So you can see in this case that for halo nucleus, the diffractive contribution is larger than the stripping one. And now, if you consider another description of beryllium 11, so which has another ground state wave function, which reproduces exactly the same asymptotics, but a different spectroscopic factor. So here is about 0.91 before it was equal to 1. So this value is not chosen randomly, is a spectroscopic factor predicted by the ab initio calculation. So you obtain this ground state wave function that has exactly the same asymptotics by construction, but very different inner part. And if you use this wave function in cikonal code, you will obtain cross-section that are on top of the cross-section in the previous case. So this indicates two things. The first one is that this observable knockout reactions of halo nuclei doesn't seem to be sensitive to the spectroscopic factor, but also it seems to be sensitive only to the asymptotics. And if it's the case, it means that you can extract A and C from knockout data on halo nuclei. So let's see how the value that you can extract compare with other values in the literature. So on the left here, you have the beryllium 11 data. So this is the beryllium 10 momentum distribution. And on the right, the carbon 14 data. Both were measured at NSCL. So if you use an cikonal model, so that completely neglects the dynamic of the reaction, you will obtain this dotted magenta line. And you can see that compared to the experimental data, the asymmetry is not reproduced. And this is due to the fact that you completely neglected the dynamics of the reaction. So if you want to improve the way we describe this reaction, what we did is that we compute the diffractive breakup part with the dynamical model, so with the dynamical cikonal approximation, and we obtain this green line. And you can see that in both cases, using this dynamical model to compute the diffractive breakup contribution is actually improving a lot the theoretical description, and the asymmetry is well reproduced, and the agreement is very good with the data. But then we were wondering how sensitive are we to the choice of optical potentials, because we made a choice, the one that seemed the more realistic, but there are other choices in the literature. So what we did is that we look for the potentials and we compute our theoretical prediction using these other sets of optical potential. And you can see that this choice actually influenced quite strongly the theoretical prediction. So we have an even larger spread for carbon 15 than for beryllium 11. But still, using all this theoretical prediction, what we can do is extract an ANC square for beryllium 11 and carbon 15, and extract also an uncertainty due to the choice of the optical potential. And the great news is that the ANC square that we extracted were in very good agreement with the ab initio predictions, no causal model with continuum. So for both beryllium 11 and carbon 15. And the even better news is that the same ANCs used in this analysis at the beginning, so the same ANC of beryllium 11 and carbon 15 does not only reproduce knockout data, but reproduce a wide varieties of reactions data. So diffractive breakup data at non-relativistic and relativistic energies, transfer data, and radiative capture data. So that means that you have one that means that the halo EFT description at next to linear order of this nuclei is actually able to reproduce a lot of reaction data. So what we kind of saw for this halo nuclei is that knockout reactions are peripheral, meaning that you only probe the asymptotics, and that the halo EFT approach is very efficient at bridging ab initio prediction and reaction theory. And to comment a bit on the plot of Tostevin and Gad that Mac was just showing. So the one neutron knockout reaction of loosely bound nuclei would be the data on the top left corner. And what we've seen is that these reactions are not sensitive to the spectroscopic factor, but are mainly sensitive to the ANC. So our analysis indicates that the good agreement observed for this nuclei is probably due to the use of a realistic ANC in the analysis. And I think that one interesting point that this study showed also is that there is a strong sensitivity to the optical potential that is needed. We should evaluate this sensitivity in a more systematic study using, for example, Bayesian analysis. So during the last minutes, I would like to address what happened when the binding energy increases. So when you go down and right. So to investigate this case, we went completely beyond the halo EFT ID. So this is not a halo EFT ID. We just consider irrealistic barium 11 bound by 10 MeV. So we are not dealing with the halo nucleus anymore. And we just use a Gaussian potential that we fit to reproduce the separation energy. So here it's chosen at 10 MeV. And by varying this parameter R0, we can generate different ground state wave function, which have different form. And you can see that the larger R0 you take, the wave function will have a larger ANC. So if you use this ground state wave function in a cikonal code, you can, as before, compute the diffractive breakup contribution, the stripping contribution, and the total knockout cross-section, which is obtained by the sum of the two. Just to clarify this here, so the distribution has been shifted to -1 and +1 just for display purposes to be able to plot all this contribution in the same plot, but they should all be centered at 0. So what you can see is that the wave function with the larger ANC will lead to the larger cross-section. So this is similar to the previous case, but to the halo nucleus case. But what is very different here is that the stripping contribution is larger than the diffractive breakup point. So if we follow the same approach as in the halo nucleus case, so we rescale the ground state wave function with the ANC, we obtain this cross-section. And you can see that none of the peaks seems to scale with the ANC square in this case. If you look at the contribution separately, so here the diffractive breakup before scaling and after scaling, you can see that the spread is smaller. So this indicates that this process is mainly peripheral. For the stripping contribution, you can see that the spread is actually larger and the order is inverse. And this actually suggests that this contribution is more sensitive to short distances. So yeah, by rescaling the wave function with the ANC, we obtain a different spectroscopic factor, and something that we can see here or that we compute, it will be more clear if you can see here, I think also, is that this wave function don't depend linearly on the this cross-section don't depend linearly on the spectroscopic factor. So then you were wondering if there was, let's say, a clear dependency of this cross-section on some single particle structure information, let's say. And we decided to look at what happens if we rescale the cross-section with the mean square radii. So this is what we obtain if we rescale the wave function by the mean square radii. You can see that in all cases, the peak is overestimated. But what is very interesting is it seems that the peak is overestimated and the tail is underestimated. So this might suggest that the total stripping cross-section and knockout cross-section will scale well with this mean square radius. So we look at that for the case where the separation energy is 10 MeV, so this deeply bound case. So the green point corresponds to this diffractive breakup cross-section as a function of the mean square radii, the blue point, the stripping contribution, and the magenta point to the total knockout cross-section. And what we can see is that there is a linear dependence or approximate linear dependence with this mean square radii that is valid for the stripping and to a certain extent to the diffractive breakup one, even if it seems that the error here are more quadratic. And what was interesting is that if we do the same plot for the halo nuclei case, you can see that we have this clear linear trend. So we have a clear dependency on the cross-section onto the mean square radii. And this can actually be easily understood by the fact that halo nuclei are very spatially extended. And so the mean square radii is strongly influenced by DNC. And so that was interesting because it seems that this knockout cross-section seems to scale with this mean square radii. And this is actually something that we were able to demonstrate it analytically also with perturbation analysis. So to summarize, the first part of this talk was focused on halo nuclei. I hope I convinced you that knockout reactions on halo nuclei are peripheral, so only sensitive to DNCs, and they do not probe the spectroscopic factor. And I think this is what explains this very good agreement for loosely bound nuclei. And let's say the second main message is that the halo EFT approach bridges very efficiently structure and reaction theory. And in this case, one halo EFT description of beryllium 11 and carbon 15 was able to reproduce a wide varieties of data. For the deeply bound nuclei, our analysis showed that the cross-section does not depend linearly on the spectroscopic factor. It depends on it, but the relation doesn't seem linear. But it depends approximatively on the mean square radius. And this actually suggests that we could extract mean square radius from knockout data. And this doesn't help understanding what happens in this part of the plot. And I think that, as it was also said yesterday, some improvements of the reaction model are still needed to understand from the reaction side what's happening for the knockout or more deeply bound nuclei. So with this, I thank you for your attention.
So thank you, Chloe. We have some questions specific to this talk before we go to the general discussion. Gregory?
Yeah, thank you. Very interesting presentation. Have you studied the dependence of the spectroscopic factor that you get from stripping reaction, the dependence on energy, at which energy you perform the stripping experiment? So have you looked into that? And is there a preference at which energy you would recommend to do the stripping reactions?
So I haven't looked into that, so I didn't value the beam energy. I guess that's what you're referring to.
Yes, that's what I'm referring to.
But my impression, this should be checked, but my impression is that so knockout reaction are somehow still peripheral, so you don't probe the whole wave function. And this is what explains this nonlinear dependency with the spectroscopic factor. And I don't think that going at larger beam energy will solve the issue.
Well, but you mentioned so stripping is more sensitive to the interior, but I think this statement is energy dependent, right? So if you go to lower energies, for example, would that still be the case? More sense, because you need to probe the interior, right? You have to have higher energies in stripping reaction. So, would lower energies be beneficial or not? That's the question.
But I think if you my impression is that knockout reactions and stripping in particular will never probe the interior, because if you are too much in the interior, let's say that the projectile and the target are too frontal, the collision is too frontal, then you will populate other inelastic channel, but not stripping. So this is my impression, but I mean, I could check and try to do some other beam energy to confirm this.
Okay, thank you.
And Thomas?
Yes, thank you for this talk. So you emphasize here that halo EFT at next to leading order reproduces these results. What about leading order?
So the leading order, you don't constrain the ANCs. And as we saw, the cross-section scale with the ANC, so you need to go to NLO.
So, I mean, even in leading order within uncertainties, it would not reproduce data, or the uncertainties are just so large?
So I didn't try it, to be honest, to go to leading order, but I mean, once you know that your cross-section scale with the ANC, it seems logical it's something that should be constrained by the, let's say, the description of the projectile.
Yes, I agree. I just wonder basically whether next to leading order really is not leading order. That's really what I want.
Yeah. Maybe Daniel has a comment because he's raised his hand.
I do have a comment. I both raised my hand and unmuted, so you knew that I was going to say something. So, so Thomas, I think you and I have had this conversation before, right? So in the study that Hans Werner and Pierre Capel and I did, we looked at the convergence, and indeed in the studies that Vijaya Acharya and I did of carbon-19, and the convergence is completely regular with respect to the halo EFT expansion parameter, right? So I would argue that if you want to estimate errors, that's actually much better than having a leading order that's right on top of the data. You want a regular convergence pattern so that you know what the omitted orders are liable to do to your prediction. I think you're muted, mate.
Thank you.
Okay, any further questions on this talk? Thomas, you still have your hand up. Do you have another question?
No, just my omission to not put it down. I'm sorry.
Okay, then maybe I can ask a question regarding this plot that was discussed in the last two talks about this correlation of the spectroscopic factors. So I mean, in both talks, this correlation was discussed. So I would be interested if there is any understanding of the physics that governs the width of this band. I mean, clearly these spectroscopic factors are not all on a line. It's a band of a certain width. Is there any understanding what physics determines the width of this band?
I'm not sure what determines the width, but the uncertainty is pretty big. So I guess it would be difficult to, on each point, to make a conclusion about the width. But maybe someone else in the audience has a comment on that.
Alexandra?
So I think the width of the band just indicates exactly the uncertainty, because if you look at what the RS actually is, it's an experimental inclusive cross-section divided by sort of the product of two models, the structure theory, aka shell model, large-scale shell model, multiplied with a consistent reaction theory that is the same for each and every point. But now, you know, if you look at the different isotopes we are looking at, they straddle across all different model spaces, right? And then some of them, you know, shell model is maybe more challenged than for other cases where you are closer to a magic number. And I think the width just tells you the uncertainty in general of using, you know, this kind of direct reaction to extract a spectroscopic factor, if you wanted to call it like that. I mean, this almost covers the entire chart. So, you know, and shell model is not equally good everywhere.
Okay, thank you. Are there any other opinions on this? Or any other questions that are left over from the talks we had in this afternoon? Please go ahead.
Sorry, this is Lee. This has to do with Danielle's talk. You mentioned the, well, you were contributing to the theory analysis of the helium-6 project. And Bob mentioned the Triton experiment that could be done in a parallel fashion. And you mentioned the uncertainties associated, the increased uncertainties due to its increased binding energy as compared to the helium-6. There's also the possibility of doing the photodisintegration of the Triton. And if one did that and did the p.p'a, would that fix some of the analysis or theory uncertainties?
Daniel, I guess that's a question to you.
Yeah. Maybe he's
So maybe he had to leave for a short moment. So from my perspective, I mean, if you did a photo disintegration of the Triton, I think you would have very similar systematics than you have in these in the pion capture reactions, and you would have a low energy neutrons, meaning having low total momentum, and in these reactions there are issues with the and as far as I understand, but maybe Miguel can also comment on that, there are issues with the neutron efficiency of the detectors and understanding that, which has a very strong energy dependence. And the whole idea of using this high energy reaction was to have the neutron pair at small relative momentum but high total momentum, where this is under better control. That's my understanding.
So yeah, I understood the experimental difficulties in say the photodisintegration at low energies, but there's actually progress made on the experimental front. So that part I understood because I'm kind of knee deep in that, but I wasn't so sure on how having both the high energy Triton beam experiment and the photodisintegration of the Triton, if they were both in hand, how that would assist a theory analysis or reduce some potential uncertainties.
Okay,
so I see Daniel.
He's back. Yes. So now you can.
Sorry,
answer.
I had to step away for a minute to answer the phone. So
let's say the question was, this is a follow-up on what Bob asked you about the Triton replacement of the helium-3. And you said, well, there's some problems with that because of the larger binding energy. Okay. But there's also, as you know, efforts to do the photodisintegration of the Triton and and measure the two neutrons. And there is progress on the experimental side as far as the dual neutron detection. But my question is, if you had both of those data sets, are they more than the sum of the parts, basically?
So the answer is yes. So because the treatment of final state interactions is different in the two cases, right? So I think you're talking about the Higgs experiment about photodissociation,
yes.
Right. So those are low energy, pretty low energy photons. So you have 3 nucleons going out at low energies. And so one would have to think that one has to do a full 3-body treatment. And so that's, I mean, that can be done, and that's interesting. One might also have to think about the role of 2-body currents in the photodisintegration. So the reaction theory is different. And so if you want to think about photodissociation as an example of reaction theory, right? And so having both provides you with reassurance that you understand both reaction theories well enough to get a consistent extraction. If Tom were here, I think he would say that you have experimental advantages to doing things with this high energy technique because you are no longer as sensitive to the energy dependence of your neutron detection efficiency.
In
Yes.
fact,
Right.
I may add a comment about that because this was the main argument, because the proposal was submitted twice to the RIKEN pack, and from the beginning the argument was that all the neutron experiments that have been done until now for the scattering length, they have in common that the neutrons are very low energy neutrons.
Yeah.
And then the neutron efficiency varies strongly at low energy. So you have to be completely certain of the variation of the efficiency. Doing this at 200 MeV has the advantage that the efficiency at 200 MeV is flat. And so you only need to measure a small relative energy, and this was achieved using HIME. So HIME, in the picture that Daniel showed, you had nebula, which is the main neutron detector in Samurai, but then in front of it you have HIME, that is a more granular detector that will provide very high resolution at low energy. So this was the main argument, and the second main argument in the first proposal was doing this at the same time for helium-6 and the Triton. So in the first proposal, the argument that was put forward to the committee was that even if there were some theoretical uncertainties, or doing this with two different with systems that are very different, like the Triton and helium-6, at the same time with the same experimental conditions, would be very strong. But the reaction of the committee was they were more hesitant on the ability of the theory that in the comparison. So I think this is why the proposal went to the helium-6 case, because this was the point that was the most discussed after the first proposal. So the original idea was doing Triton and helium-6 at once, which technically is very relatively easy at RIKEN. But the pack asked to be more certain about the handling of the theory, and I think this is why helium-6 remain as the main reaction.
We concentrated on the helium-6 theory for various reasons. We could do the Triton theory, and Hans Werner, in fact, was involved in work almost 20 years ago to carry out the Triton calculation to higher orders. So although the leading order calculation may not be as accurate in that case, one has the advantage that one has some of the higher order corrections like we were discussing with Thomas. And so in some sense, we already know more about the convergence pattern for the Triton. But yeah, so the theory could be done for the Triton. It just Matthias, Hans, and I, and Carlos Bertolani and Tobias Federico concentrated more on the helium-6 case so far. So that's yeah.
Maybe if the experiment goes well with helium-6, then there will be a second part of experiment after with Triton, and then we will have. So this idea was a risky idea because it was very original, and I think that RIKEN was afraid of taking the risk. And then, well, maybe if Tom demonstrates that it works, that it can be done, and it's sensitive, then I think that the Triton experiment could come after that.
Yeah, I mean, I think if it works, there are other interesting things one could try, right? So it's because so little is certain about the neutron-neutron interaction that, you know, having a new approach would be fantastic, right? So, yeah.
But the primary problem with the photo disintegration of the Triton then is the experimental one of not having a flat efficiency region in the region that you are probing, that you're experimentally using.
That is my understanding. I mean, as well as the whole Triton target issue, right? But that's a That's a
Right,
separate.
yeah.
Right. I mean, so I know that for the pi minus d to gamma nn experiments, which I spent some time, let's say, sort of analyzing and working on the theory for in the aughts. So there, that was the key, right? That was essentially the limitation on, yeah. So
Yeah, I get that. Okay, thank you.
yeah.
Maybe I could also add a comment on this proposal at RIKEN. I think one important point that we didn't get across well enough in the first round was that, I mean, the whole experiment. So there were some doubts that you can describe this reaction at a level of accuracy that is good enough to have a meaningful extraction of the neutron-neutron scattering length. And of course, it's true that in a general case, describing this reaction is very difficult. But this experiment is designed specifically as a high energy reaction in such a kinematics that the only final state interaction that happens essentially is the one between the two neutrons. So the experiment is designed such that you can do the theory. And this point we had to improve on quite a bit. And but it would be the same if you do the experiment with the triton in that kinematics.
Yeah.
Okay, are there other discussion points?
I had another question about the first talk, Simin one. So it's very beautiful to see how the wave function, the internal wave function, evolves in time, and how it changes, and how it becomes the final state that you detect. But is this link unique? So can you be sure that another internal wave function will not evolve into the same one that you are detecting? I mean, is there an ambiguity when you see something? Can it come from two different internal wave functions that have evolved in the same to the same final point?
I would say that the final point has larger uncertainties. So because those are distorted by the current wave functions, which almost make every distributions like more widely distributed. So it's hard to tell which partial wave is actually coming through. But we need to study more cases to make sure that to make sure those structural information is properly described, I think.
Thank you.
Thank you.